All right. Seems we're live. We got a spring session coming up for you in those next like 50 minutes or so. A welcome from my side to the Spring Framework 5.2 session. My name is Juergen Hoeller. I have the pleasure and the privilege to serve as the Spring Framework project lead for 16 years and counting. So I'll provide very much an inside view for you here today. And this particular session reflects a couple of recent work streams of ours in the core framework team at Pivotal that I lead. Core Container Revisited really means that it means two things. For the purposes of this session, we're going to revisit a few perspectives on core container in the largest sense of the term. We're going to talk about, of course, the actual core container a bit, the application context level in Spring, but also about the endpoint models. So we are going to touch upon Webflux, WebMVC, even RSocket endpoints, so messaging endpoints, and a few other bits as well. And there's also a bit of a performance section in the middle. This is a very personal selection. This is not a what's new in Spring Framework 5.2 or 5 in general, but it can serve, of course, also as an introduction to recent enhancements at Spring Framework level in 5.0, 5.1, and 5.2. So there's quite a bit of it is related to recent work from the past 2 years. There are quite a few things that are 5.2 specific, but actually I guess the better part of the presentation is equally applicable to like 5.1. All right, so much for the purposes of this session. A forward reference, just so that I don't forget. There's a live demo session this afternoon by Josh Long called Reactive Spring. I very much recommend going there as kind of a counterpart to this one, a very different perspective, a live coding experience, very much driven from the Webflux angle downwards. All right, so let's begin with the first of my 3 sections, the core API revision. From a framework authoring perspective, evolving a framework API is of course a non-trivial task over the years. And as you may be aware, the Spring Framework has its roots back in, well, effectively 2003 under that name. And 2003 was a very different era. JDK 1.3, 1.4 just emerging. Pre-Java 5, pre-Java 8, of course. So the core API revision is something we have to do every couple of years. And we take the opportunity for every major release of Spring, also in the sense of semantic versioning from an API perspective and a baseline perspective, to raise the Java baseline and to embrace everything we have in that baseline. And with the Spring Framework 5 generation, this is of course Java 8. It's not exactly brand new now, but 2018, 2019, those are the years when the framework and the library ecosystem at large is really fully embracing Java 8. And I'll summarize a few things we have been doing recently there. Some of them might be obvious, others not so obvious. Just double checking, who's actually on Java 8 in production at the moment? I guess that is still a majority. Inverse check, who's on something newer, say something newer than 8? Okay, of those, 11? Anyone on 13? 12 or 13? Oh yeah. Well, that roughly reflects what I thought it would be, thanks. The industry baseline, of course, in many ways is Java 8 still. But let's not forget, Java 8 is already like 5 years old and not exactly the latest generation of Java. But as framework authors, as framework providers, we're also stuck basically where the world is at large, right? Where the industry is. We're a very pragmatic framework or a set of frameworks, and we need to pick up the industry where it's at. And this is largely Java 8. But fortunately, the Spring Framework 5 opportunity we had like 2 years ago was to raise this baseline at least to Java 8 level. And that means a lot to us, because we can, of course, internally use lambdas and method references and whatnot, right? for the entire code base. You might not have noticed, actually, as people started using Spring Framework 4, Spring Framework 4.1, 4.2, 4.3 on Java 8. The framework generation back then, for all intents and purposes, in practice, it felt like a Java 8-oriented framework already. But it was internally Java 6 baselined with lots of optional Java 8 support, kicking in at runtime automatically just by you choosing to run a Spring-based application or to develop a Spring-based application on Java 8, against Java 8. But only with Spring Framework 5, we're able to internally embrace it. There's quite a bit of user value as well here. It's not just us internally being able to optimize a bit of code. There's a few runtime implications. We, of course, make use of the latest API advancements within the JDK, in particular in reflection, and in the NIO APIs, where existing Spring features and Spring functionality, Spring methods, even down to the fine-grained level, now make use of kind of the best possible way on Java 8 and higher to kind of translate your request, your intentions into runtime behavior. Whereas other features in Java 8 are more visible to you at the application development level. Quite a few framework APIs now have like overloaded methods. They take they return completable future results. They take the java.time types as arguments, like on task scheduler, on quite a few methods across the code base where this makes sense. If you look at recent versions of WebMVC, HTTP headers and related APIs now have overloads where they accept HTTP header values directly as java.time types, for example. That's the sort of stuff. Another one that we're going to see in just a moment is the use of Java util stream. We not only support a few API types, we are trying to embrace the Java 8 API style, right? The style that Java introduced with collection streams in Java 8. This is a certain API style, a sort of functional API style that we're trying to follow and that we're trying to expose from Spring Framework APIs where this makes sense, where we kind of connect to that API story. And there's another little one, the use of default methods. There's many things we were able to do, to your code in particular, before Spring Framework 5. If you started using Java 8 constructs, we did everything we can automatically, using some optional code, using some reflection. But there was one thing we could not do before Spring Framework 5, and that is declare default methods in interfaces ourselves. And now with Spring Framework 5 having that baseline, this is ongoing work. So there was an initial bunch of default methods in Spring Framework 5.0, then in 5.1 and a few more in 5.2, where we redeclare existing interface methods. That's actually the most interesting part, where we redeclare existing methods for convenience purposes. Like beam postprocessor, handler interceptor in WebMVC, in particular callback interfaces with several methods. You might only want to implement one. Previously, you had to stub out the others or extend from some adapter class. None of this is necessary anymore because there are default methods in those interfaces that basically express no op, and all you have to do is implement the methods that you're actually interested in. So using a Java 8 language feature, default methods, for convenience purposes in framework SPIs is what we're aiming for here. But the other, more traditional default method benefit is, of course, applicable to us as well. We add new methods, if we can, with default methods on existing interfaces so that the existing implementers of those interfaces aren't broken. All right, so that's just a bit of insight into what's possible with Java 8. Very closely connected to this is a nullability story. That's actually almost a bigger deal. Well, I guess it is simply the bigger deal. Along with the Java 8 API revision, we went through the entire code base and redeclared nullability using formal add nullable annotations with a non-null by default rule. Why do we bother? Right? Why is this a thing? Well, in traditional Java, of course, nullability is not well specified. You can't express it at the language level. Any method you're calling could return a null value. a primitive return type. Any incoming arguments could potentially be null. You never really know until you check the Java doc, and then you hope that the Java doc is actually right. And then you hope that the implementers of those methods are actually adhering to the Java doc. So this tends to be a bit of a mess, and we as framework authors know. We're calling many other APIs from other frameworks, Solid API, Hibernate, whatever, and we always have to defensively handle these null scenarios. So from the perspective of presenting an API service to you, in Spring Framework 5, we decided to be stricter. We have now non-null API by default conventions expressed at the package level. Any exceptions to that rule, meaning any argument that can be null or any return value that can actually be null, is now annotated with @nullable, with an annotation, a formal annotation. It's also usually expressed in the Java doc, but the annotation is a formal element that you can even check at runtime if you want. And it's something we can validate using tools. It's also something you can validate using tools against our APIs. We really grew fond of IntelliJ IDEA's support here. IntelliJ IDEA's nullable handling, not just the base nullable handling, but the constant conditions and exceptions inspection in IntelliJ IDEA is really super useful. That's what we use internally. So basically, we check our entire code base with that inspection, making sure that we're not missing anything. Basically, every code path, every call stack through the code base is validated by the tooling to make sure that you're not missing a potential null pointer exception. And also the other way around, that you're not overly defensive. Basically something that will never be null according to the declarations. Why do you have to have a non-null check in your code? Right? If it can never be null, if it's formally proven to never be null, as long as calling code adheres to the nullable declarations. That's what we're using internally. If you're calling our APIs or providing integrations with Spring APIs, that's something you can use as well. Because IntelliJ IDEA understands our annotations by default. It also understands other sets of nullability annotations that you can use in your code, and then you can validate the assumptions that your code has against the declarations that the framework code has. That's not only true for our APIs, it's also true, for example, for RxJava, for OK-HTTP. So we're really joining a bit of an open source industry trend here. Aside from a plain Java story, there's also a Kotlin story attached. And this is actually part of the motivation of why we're doing it. Because in Kotlin, the Kotlin compiler, the compiler has a stronger nullability handling. You can declare a variable in Kotlin as non-null. The Kotlin compiler will only allow an assignment to such a declaration from a Java method call if it can formally prove that the Java method will never return null. So the only way for an idiomatic Kotlin story calling into our Java APIs in terms of nullability handling, the only really clean way is to declare those nullable annotations. That was part of the motivation of why we're doing it. Right, there's some ongoing collaboration. There's a well-defined annotations project with Google, JetBrains, and others. So this is an ongoing story. There might be some further libraries coming along, joining that club. So before we move on to other topics, just a couple of visual impressions of what this can mean. Where, for example, here these methods on the object provider interface, which is a kind of fancy handle to a target dependency. So just, I'm only really using it as an API example, but the purpose of object provider is basically, instead of injecting a direct reference to a dependency of type foo, you have an indirect handle, an object provider of foo, where you can lazily obtain the instance, or if it's not singleton scoped, you can lazily obtain a current instance, and you can do some fancy interaction with the container, only give it to me if it's actually available, only give it to me if there's a unique instance, if there's not more than one, that sort of stuff. Those methods were there before. They date back to the Spring Framework 4 line, for the 3 at least, where some of those APIs have been revisited. And now in Spring Framework 5, there are fine examples for where nullability annotations kick in. They are redeclared now with an @nullable return value. Because according to their documented semantics, getIfAvailable says if it's there, give it to me, otherwise return null. That's what the Java doc said before. Now it's at nullable in terms of its actual declaration. And combining these two kind of work streams, these revisions of the core container, you can see them in action with a few new methods here. They actually declared as default methods for a start. They use some Java 8 API types, Java util function supplier. In terms of its role is kind of a key common piece of a callback element in the Java 8 collection stream model. So we are using the same interfaces. And these methods are basically more Java 8 minded. Instead of saying get if available and doing a not null check, you could call get if available and pass in a Java util function supplier that produces a default instance if it's not available. With that setup, the return value will never be null. And so it doesn't have at nullable, non-null by default in our setup. So that applies to both variants, get if available, get if unique. There's a slightly more functional version of it, a variant of it. It's this if available. If available, and the Java util function consumer says, in a more functional style, if it's available, give me a callback to this consumer. Let me do something with it. Otherwise, just skip that step. So that's also quite in the direction that we're going with some of our APIs. And combines the nullability rules with Java 8 API style here. Even further down that line, more recent methods, there's support for iterating over several matching beans on object provider. So if you say object provider of foo, you may also interact with the container in terms of going through all or selected matching instances of foo if there's more than one. And those come in traditional form with like iterators. But the more interesting ones are stream and ordered stream. Returning a Java util stream and basically giving you a chance to express your selection rules, the instances that you actually want to see through basically stream interaction, the same way you would do it on a Java collection. And there's two distinct versions because ordered stream is a little more aggressive in terms of initialization, whereas stream is totally lazy. Ordered stream is not entirely lazy in order to arrive at its ordering rules. But that's also a fine example for what we're doing here at the core API level in recent generations of Spring. Now, this is not the main topic of the storyline today. It's more of a reminder. There's also another side to this equation. Any beans that you can interact with have to be defined at some point, right, on startup usually. So the object provider API is an API that you interact with in a fully initialized container in order to find out about matching instances, delegates, collaborators in the context. On startup, you may also programmatically register beans. So assuming again a fully functional style setup, you could instantiate a generic application context and say like register bean, default rules for class foo, register bean for bar.class, but there's a special rule. Whenever you need a new instance of bean, here's an instance supplier, again a Java util function supplier, that produces a fresh instance, a new instance of bar in this case, whenever the container needs it. So that's also kind of an interesting twist. You can register beans in many ways, right? Reading XML bean definitions, you can send the container on a class path scan to find matching instances according to the annotation-based component model, or you can register beans programmatically. It always ends up with the same bean definition model in the core container underneath the covers. But this is a really nice complementary style to programmatic interaction with the container. Programmatic registration of beans on startup. For example, could be a test setup, but it could also be a sort of small service, a microservice style architecture where you only build small application contexts with a few beans, maybe a dozen beans. A dozen beans can still easily be registered in this style. By the way, the container is still in charge, of course, of everything else, right? The life cycle, extra rules, post-processing, all of this still applies. It's literally just a sort of replacement for a factory method that we're building here. We're just instructing the container for how to create a new instance of this bean, just like an add bean method in configuration classes, expressed in a functional callback style. And there's a slightly fancier version down here with a method reference that avoids reflection for instance creation for the default constructor call. This is slightly fancier. It assumes that bar takes an object provider of foo, and there's another callback that we call a bean definition customizer, where basically anything else you want to set, you can do in a callback where a bean definition comes in, just do something with it. You can have any number of those. So it's a nice way of a single call with 2 inline Lambda expressions arriving at a fully configured bean definition eventually. Also not the main topic today, but there's of course an equivalent Kotlin style, also for the interaction APIs, but it's a little more, the difference is stronger on the registration side. This is basically the same kind of code, but it's using Kotlin extensions that we provide out of the box. So also a reminder, if you're using Spring Framework 5, you get Kotlin extensions in the canonical Spring jars as you get them from Maven Central. We ship Kotlin extensions to many core Spring classes. The Kotlin compiler automatically picks them up. So if you use generic application context from Kotlin, you'll see extra methods on it, overloaded methods that take K classes and K functions for a slightly more idiomatic Kotlin experience, similar to what we've seen before, but it's not actually Java Lambda expressions, it's Kotlin functions being used here. You have to repeat yourself a little less because a Kotlin function reliably returns at runtime that the kind of return type that it has, something a Lambda expression cannot do for us. So you don't have to say bar.class and here's the Lambda. You can just declare a K function that creates a bar instance and you're done. And this is playing with the Kotlin language style, a little bit like the Gradle DSL for the Kotlin DSL for the Gradle build tool. It's not an official name, where the same kind of calls can be inlined. All right. So all in all, the API revision efforts in Spring Framework 5 are almost complete. Between 5.0 and 5.2, we've basically done almost everything we meant to do. So we're almost there. We revisited almost every place. The Kotlin story is still a little bit completing because Kotlin is a moving target with Kotlin 1.3 right now. And the coroutine story, also not a topic here, but Kotlin coroutines have special support on Spring side as well, a very recent feature. All right, let's move on to the performance topic. I've got a third one, the recent advancements in the reactive endpoint models afterwards. So performance tuning is, of course, a never-ending topic. When are you ever done tuning for performance? There's a couple of traditional kind of features in Spring or scenarios in Spring that you're trying to optimize. A good old one is a warm-up. It's actually not old, it's 5.0, 2 years old. In component scanning, whenever you send the container on a component scan, so whenever you instruct it to actually search your class path and find matching components, something you have to do explicitly in Spring. At Spring Framework level, totally explicitly in Spring Boot by convention. But you don't have to do it, reminder. You can register beans functionally without any class path scanning, any reflection even, any annotation retrieval. But if you choose to do this, typically in combination with the annotation-based component model, there's a dedicated component scan instruction, and we usually recommend to narrow your base packages. Because when you want us to find components everywhere, we literally have to search the entire deployment layout, the entire class path. By giving us base packages, you significantly cut down the effort. As a kind of mediating solution in between, we have an annotation processor called the Spring Context Indexer in 5.0 and higher, where we basically create a little spring.components meta in file, enumerating the classes that match the conventions in your deployment layout. You'll include that file in your jars, and at runtime we'll basically look for those files. If they're there, we assume that they are correct and complete, and perform your component scan against those files instead of searching the class path. unless you're doing something unusual. But with standard include and exclude filters, that's what we would be using. So that's one example for an existing feature where you can take a Spring-based application setup and optimize its startup performance in certain scenarios, if startup performance is actually a critical path for you. In Spring Framework 5.2, very recently, we revisited, actually re-implemented our entire annotation processing. So when you're using Spring Framework 5.2, upgrading to 5.2, you'll implicitly get usage of what we call the Merged Annotations API. This is a restructured annotation retrieval API for Spring conventions. Spring has a meta-annotation model where you can compose your own annotations. Your own annotations can be meta-annotated with standard Spring annotations. These kinds of arrangements are sort of expensive to handle at runtime, and the Merged Annotations API streamlines certain interaction use cases that Spring has, and has, well, somewhat more efficient caches for those purposes. The existing retrieval APIs in Spring, annotation utils, annotation element utils, and co, that all the Spring extensions and Spring itself out there has been using for many years, are basically delegating to the Merged Annotations API underneath now. So you'll get most of the benefits implicitly. Some of those implicitly by upgrading to 5.2, of course. So some of the design purposes, the design we had in mind here, is we'd like to enable alternative ways of storing annotation metadata. There's the topic of like registries, indexes, like a Gendex index that exists at runtime, and we could get the information we want out of the Gendex index as well if it's there already. Makes most sense if the Gendex index is also used by other tools like by Hibernate, where we could reuse that information. We haven't actually shipped the first class version of this yet with user level API, because in our experiments, in our benchmarking, we haven't found a significant enough difference. Generated indexes are a build time step that produce a large and complex extra file that we need to parse on startup. And parsing that index in our tests, in our benchmarking, is almost as expensive as performing reflection. So it didn't really lead to any significant gains. But there might be something coming along those lines, more as an integration scenario where not only Spring, but Hibernate checks and whatever else it would be. If they all agree to use the same index, then the benefits materialize a little more, a little stronger than if it would just be Spring using a multi-megabyte Gendex index. But that's kind of a bonus topic, the whole index stuff. Most of the efficiency improvements for annotation retrieval through reflection are available as an upgrade to 5.2 without you having anything to do beyond that. That said, there's a limit to what we can improve in terms of just implicit refactorings and improvements underneath the covers. In some ways, it's you and your components asking us to do expensive work that we cannot avoid. The component model comes with certain assumptions and certain rules, like configuration classes with their add-bean methods. If that's how you declare your beans, we have to handle the configuration classes, we have to reflectively call the add-bean methods, we have to find out about them up front. There's only so far that we can go in terms of optimizing this. Actually, the annotation part is not that expensive. Configuration classes come with an extra feature where you can call some of your add-bean methods from other add-bean methods. So you have multiple add-bean methods, and you do inter-add-bean method calls within the same class, or even from one add-bean method you delegate to some other configuration class, some add-bean method there, and you expect the container to intercept these calls in order to perform its lifecycle management, proxying, post-processing, whatever needs to happen, right? Those look like straight method calls, but they're actually intercepted to go back to the core container and get the current bean instance for that target call. In order to do this, we have to create runtime subclasses for every configuration class of yours. Might not matter if it's only a few classes. If you provide us with a couple of hundred configuration classes, this could get expensive. Imagine a Spring Boot scenario where many configuration classes exist out of the box in Spring Boot itself, in Spring Boot auto configuration, and then a large application may add quite a few decomposed configuration classes to it. in order to avoid runtime generation of those subclasses, you could opt out of this special feature, the add-bean interaction feature, by saying proxy bean methods false. Many Spring Boot 2.2 configuration classes do this now. This mode of interaction existed before. If you're using add-bean methods on non-configuration classes, you already had that behavior, but now we have a configuration stereotype version where you opt out of that specific feature, primarily for performance reasons. There's no other benefit, it's just performance. Since CGLib proxies are also generated by the AOP framework, among other more esoteric corners of the container, that's where CGLib is mostly used. Target class proxies in the AOP framework, also used for like edge transactional processing, for example. Well, it's worth mentioning that interface-based proxies are more efficient. You might want, for performance reasons, for performance-critical service bootstrapping, you might want to use interface-based proxies, which you can through opting out of proxy target class. Actually, interface-based proxies are the default for core framework functionality in most places, but it can be overruled in higher level configuration. Interface-based proxies are a standard JDK feature. So aside from being more efficient to generate on startup, it's also more forward compatible with JVM variants where CGLib doesn't work. So that's those are features, performance relevant features where we need your support. We basically need you to slightly refine your component declarations in order to allow us to do a more efficient job on startup. Right. I've already mentioned third-party libraries. Just a quick note that whatever you optimize at Spring level might not actually materialize in terms of much performance gain on startup if other libraries that you're using, other frameworks that you're using, are expensive to start up on their own. And the persistence provider, like the JPA provider, mostly talking about Hibernate ORM here, are very, very, very expensive. So in a typical Spring-based application setup, it might easily be Hibernate eating up more than half of the startup time on its own. So whatever you optimize in the rest, if that half remains the same, you might not get a significant enough difference. Fortunately, recent versions of Hibernate, particularly recent 5.4 versions, have some, even in the maintenance releases, they are sneaking some performance improvements in, but they are mostly opt-in. They also need specific configuration and some fine-tuning in the way that you declare your entities occasionally, or the way you intend to interact with Hibernate. But it's mostly a configuration story. If you switch to bytecode enhancements instead of runtime proxy generation, in Hibernate, for Hibernate entities, you get kind of a unified modified class for every entity class. This can be significant in a large application on startup. And of course, it has index integration of its own, which you might want to use. Jackson is also another kind of expensive one, right? Any kind of data binding framework introspects every class that you are potentially binding. So it needs to find out about the structure of that class and how to bind to that class. The only recommendation I really have here is, well, first of all, try to be on the latest Jackson. They are also, based on our feedback, they are doing a lot of improvements internally. So try to be on Jackson 297 and higher. That's actually our new baseline, but try to be on Jackson 2.10 if you can. And the only opt-in kind of way of improving Jackson's performance is switching to an alternative data format. If it doesn't have to be plain JSON, why not go for like Smile or CBOR? Standard support in Jackson is available. That are just more efficient to parse at runtime. There's only so far you can go in terms of JSON binding performance if it's always the standard textual JSON arrangement. All right. So before we move to the final section, revisiting reactive for a few minutes, two forward-looking notes that I'd like to send your way. We are working on GraalVM support. We have been working on GraalVM support for quite a long time. GraalVM comes in two flavors. GraalVM is many things. So in a nutshell, it comes in two flavors. As a JIT, as a just-in-time compiler that can replace traditional C1, C2 in hotspot on OpenJDK. It's even out of the box there in OpenJDK 11 and higher. So that's one thing that it is. It is a language adaptation framework in the form of its truffle component. That's not our story today. And it also comes with a native image generation tool, where you can turn a Java-based application into a native image that basically contains everything that's needed to run this Java-based code out of the box, with predefined classes, with pre-arranged resources. There's not much dynamic optimization going on, if any at all. It's basically a pre-generated image for almost immediate startup and pretty low memory consumption, at the expense of, well, some peak performance, right? A regular JVM with hotspot is really good at optimizing for peak performance. That, of course, means that your JVM needs to run long enough to actually reach peak performance. For short-lived processes, in the most extreme case, function as a service calls, but even short-lived bootstrapping of extra instances in a cloud scenario, in high load scenarios, that sort of stuff, where some of those instances might not live very long, then it does make sense to optimize for startup performance and to sacrifice peak performance. And the native image model can be a solution to this. The underlying Graal component called SubstrateVM is at this point still an early adopter sort of plugin. It's sort of there in the recent first GraalVM GA release, but a bit of an extra installed early adopter thing still, right? It might become more of a prominent tool at the forefront in the GraalVM 20 release next year. So what we're working on here is, at the moment, we're documenting all the rules, constraint restrictions, and all the extra configuration needed for building a Spring-based application that is meant to be deployable as a native image. This really needs to be something you are architecting for. You cannot just take any Spring-based application or Java-based application, for that matter, and turn it into a native image. There are many things that don't work in native images, or they don't work the usual way in native images. SubstrateVM does support reflection, but it needs build-time reflection configuration. It needs to know which classes you're going to reflect upon at runtime. Same thing is true for proxy generation. As long as you instruct it up front for which classes are going to require proxies at runtime, it can pre-generate them and include them in the image. At the moment, this is basically manual guidance that we're providing here. We are working towards a more of a first-class story here in the 5.3 timeframe, basically towards second half of next year, where we would provide like build time tasks that produce GraalVM native image configuration out of the box that basically apply Spring conventions, and instead of you hand coding those configuration files, we would generate them for the standard cases so that there's a bit of a streamlined story here. Keep in mind, this is a deployment model, it's not a development model. Native image generation takes minutes, even for small applications. So you're not going to do this in development. But you have to architect for it if you're trying to deploy it. You have to have really good integration tests at the end of this chain. Yeah, it's a totally exciting feature. I mean, what they do at the technical level and what benefits this can bring to Java-based to Spring-based applications is really exciting from a technical level. We'll have to see where this is going in terms of where it brings the right benefits and compromises, where it's the right choice to make in enterprise scenarios. We'll all find out as we move into 2020. We have a good collaboration with the GraalVM team at Oracle, coming out of Oracle Labs. So we are very closely working with them in making sure that both GraalVM and our kind of alignment with it go into the same direction towards next year. So at this point, this is still experimental, but quite an interesting way of radically optimizing startup performance in particular. Right, so last but not least, in Project Loom, we have a kind of interesting feature to come up in OpenJDK soon, right? It's there in an early access version, a separate variant of OpenJDK, where we get fibers. This is, of course, not optimizing for startup performance. We're back in peak performance mode again. in a highly loaded JVM with many concurrent requests coming in, the thread-based model is really maxed out very quickly. You can only set up Tomcat and co for a certain maximum number of threads. Any further requests coming in with all current threads, all current worker threads being blocked means you have to reject them or make them wait, right? The fiber model promises to bring benefits to existing thread-based setups, to existing traditionally structured APIs with blocking API interaction for I/O, so for like for servlets, for JPA, for standard JDBC interactions. The benefit of fibers is basically implicit. You deploy your JVM with fiber mode, in fiber mode. It switches to a lightweight user mode thread model, where you can scale these lightweight threads to a radically different degree, any number that you want, basically, tens of thousands easily, on the same JVM. And they're managed within the JVM. The primary benefit here is that existing blocking API, imperative API interactions can be radically optimized in peak performance scenarios. There won't be a difference in loaded services at all, right? It's more like for certain kinds of target services. But this is one of the technically most exciting improvements in OpenJDK that we're waiting for. Could bring some new fresh life to Spring MVC after all, and to traditional JPA JDBC interactions. With that said, let me wrap up my storyline here with a few notes on reactive. Of course, reactive is the other solution to the problem, right? You could try to stay on a thread-based interaction scenario like a web MVC application and try to optimize it, or try to use fibers once they become available in regular OpenJDK. Or you could go a different way and optimize in particular peak performance scenarios, highly loaded scenarios, certain endpoints where you find lots of your clients are currently blocking. You're trying to re-architect them towards a reactive interaction model where your endpoints, and this is the traditional example, right, for a web endpoint, where the endpoints don't process the request, kind of call blocking APIs until they get the results, and then they generate the response, and then they're done. The purpose of such handler methods, this is a typical reactive web endpoint in like Spring Web Flux. The point of those methods is different. They build a reactive pipeline, a set of instructions for how to arrive at a response. They return it back to the runtime infrastructure, and the runtime infrastructure is trying to have a non-blocking arrangement where it's only going to call back into that pipeline for the next steps as data becomes available and can be processed without any blocking. This is, of course, comes with many benefits. There's a reactive streams architecture underneath the covers. There's back pressure interaction with the underlying I/O components, like with your data store driver, and also back pressure interaction with the web infrastructure, with a reactive streams-based HTTP kernel. Now, we're not going to discuss general benefits of reactive all that much. What I'd like to show you today still here is a few variations that you might not be aware of in recent Spring versions here. A controller like this one, basically a reactive web controller, is designed for WebFlux. On WebFlux, generally speaking, right? On WebFlux, you're going to have to declare all your endpoints as reactive endpoints exclusively, because it runs on an event loop architecture. You must not ever block the event loop, right? So in WebFlux, you get the pure, most efficient runtime incarnation of this. And also the strictest one in terms of adhering to its conventions. You might not be aware that you can use the same methods, the same method style in WebMVC. So what happens if you declare such a controller with reactive endpoints, building a reactive pipeline, reactor mono and reactive flux types in this case, if you deploy it to a Spring MVC application? If it's the Spring MVC dispatcher servlet starting up, finding such endpoints. Well, we're trying to do the best we can to translate them into appropriate runtime behavior. We basically take the endpoints. We know that they are reactive. We switch the servlet thread into async mode, into async I/O mode, and adapt the async I/O APIs in servlet 3.1 to reactive streams underneath the covers. There's even a degree of back pressure with I/O availability here. So This is actually a quite nice and straightforward translation of what you're giving us here with what the servlet container can do with it. So reactive endpoints work on a servlet container. You can even mix and match them with regular endpoints that do JPA, JDBC, whatever. So the web MVC on servlets is kind of the common ground. Some endpoints can be reactive if they need to be, if you want to code them reactively, or if you need to optimize them and you choose to use reactive programming for this. You can mix and match on Spring MVC accordingly. Whereas on Webflux, everything has to be reactive, right? Quite a different proposition. All right, there's a little bit more we're doing in that direction. You might have noticed that we launched a separate project called R2DBC, currently Pivotal sponsored. It's basically a kind of reactive version of JDBC, an API for relational database interaction based on reactive stream semantics. Spring Framework 5.2 doesn't come with R2DBC support out of the box, but Spring Data More does, the corresponding Spring Data release. And there's a little bit of functionality at Spring Framework level that interacts with this nicely. Like, what if you do this? You declare a reactive service method in like some service class, and you stick @transactional on it. What we used to do is, well, we're going to intercept the call, set up a thread local, bind a transaction according to your transaction manager to the thread. We call that method and we commit or roll back afterwards. Does that make any sense with a reactive method? Not really, right? These build pipelines, they don't do anything. They don't do any data store operations within the calling thread. So in 5.2, we have a different way of interacting with them. We understand it's a reactive method. And we have a different mode of transaction processing called a transactional operator. We essentially decorate the returned pipeline with a transactional operator that adds a transaction context at the beginning of the interaction chain, and at the very end, it commits or rolls back based on that transaction context. And further down the line, operations further down the line may pick up that transaction context and interact with it, with the resources in it. And that's exactly what Spring Data R2DBC does. That's what Spring Data MongoDB can do. That's what Spring Data Neo4j can do. So all the drivers with, all the reactive drivers with reactive transaction support can interact with this nicely. So it's the best we can do with a declarative transaction in a reactive architecture. There's a bit of SPI arrangement behind this, where of course, you cannot just use your old transaction manager with this, right? There needs to be a dedicated implementation of the Reactive Transaction Manager SPI. And as mentioned, we basically have 3 of them, all of them coming in Spring Data More, R2DBC, MongoDB, Neo4j. You need to configure those reactive transaction managers. You need to let us pick them up. But we pick them up according to the same conventions at Enable Transaction Management, and we just move along from there. All right. The last major one I have for you today, is reactive messaging. It's a bit of a gap we had before in the Spring Framework 5 reactive arrangement. You could use it at many levels, in particular also for web endpoints, but Spring Messaging didn't really know what to do with reactive endpoints. As of 5.2, it does have a reactive interaction model, so there's a way to use like message mapping annotations on methods with a reactive return type. Of course, you need to have appropriate runtime infrastructure underneath the covers. This doesn't work with JMS, right? But it does work with reactive interaction protocols. Most importantly, with RSocket. So there's RSocket is another industry initiative, a collaboration with participants from Facebook, many others, and Pivotal as well, where RSocket basically models an interaction style based on a reactive streams architecture for different interaction models over a messaging protocol with a transport abstraction underneath. And our RSocket bindings are just a nice way to declare Spring endpoint methods with message mapping annotations and a very immediate adaptation to the RSocket setup that you chose for us underneath the covers. So there's dedicated presentations about this. It's needs a lot of introduction. If you check our blog or even on YouTube for RSocket Spring, there's like quite a few in-depth presentations on this if you're interested. Right, and there's another little gap that we've been closing. If you have event listeners, application event processing in your architecture, those didn't really know what to do with reactive return types either. And now we close that gap. For an event listener method that declares a reactive return type, we basically consider this a follow-up event or a completion signal that we subscribe to, and we publish the follow-up event when your reactive pipeline is done. Runs on the reactor scheduler as you would expect. So another little gap that we've been closing. Right. Since we're at the end of our time, just a very quick note that whenever I say reactive type, I mostly mean reactor monoflux as the primary API types. You can choose to use RxJava. You can choose to use implementations of Java util concurrent flow if you find any out there in the wild. You can even use completable futures, kind of a simple one-element sort of reactive return type in most places where we support reactive types. And as of 5.2, again, a separate topic that we have dedicated presentations on, you can choose to use Kotlin coroutines that we automatically adapt to our reactive streams architecture underneath the cover with the same infrastructure. A different language style of declaring is effectively reactive interaction with the underlying messaging system or the underlying web architecture. All right, let's wrap it up here. Pretty much everything I've been showing here is available now in Spring Framework 5.2. Just went final a couple of weeks ago. There's also Spring Boot 2.2, bringing all of those things together. It's actually was just released this very week in its first GA form. Spring Boot 2.2 is, of course, the primary entry point into all of this, bringing together not only Spring Framework 5.2, but also the features in Spring Data More, first-class RSocket support. It's kind of the preferred entry point for consuming most of those development features that I've been showing or hinting at today. All right, so thanks for your attention. I know that's plenty of stuff and a diverse set of topics. I hope there was something in it for each and every one of you. If there are any questions, I'm around all day today. But if you want to have some immediate conversations, I'm also here for the initial part of the lunch break. So just come up to the stage and we'll discuss any questions you may have. Please stay tuned in terms of our blog, spring.io/blog. There's quite a bit of stuff coming until the end of the year still, the Spring Cloud releases and so forth. So it's a very busy period in our engineering groups, and I hope what we're doing here actually connects with the problems that you have in your applications, in your services, in your systems. So thanks and enjoy the rest of the show.